Hi everyone. Today we will discuss about the biasing of MOSFET and the common source amplifier. So let's go to the biasing. So for this, let's build one amplifier. So the voltage controlled current source amplifier we can make. So for making this, there is some V in. Okay, this is plus minus V in, and here is a KV in, which is voltage controlled current source, and here I am giving RL. So taking output across this V out will be equal to KV in RL, means KRLV in minus. Okay, so if V in is equal to this, so V out will be equal to this. Okay, so see, this much is the amplification in the V in. So that's why it is like this. This is V out, this is V in. So this is voltage controlled current source, and we can create this with the help of the MOSFET also. MOSFET is also a voltage controlled current source. Okay, so we can create it like this. There we can give input, and there is RL and V naught. So this is an amplifier made with the help of the MOSFET. Okay, so this is V in. Let me take another pen, this green pen. So this V in is like this, and the value of this point is 5 millivolt is the amplitude of this V in. Okay, this is 0 and this is minus 5 millivolt. Okay, this is V in. Now let's make ID versus VGS. ID, and this is like this. So this is VTH 0.5 volt I'm considering. So this V in will go up to here, around somewhere here, which is 5 millivolt. Okay, and it is not reaching up to VTH, so the MOSFET will remain off. Okay, for making MOSFET on, we have to give VGS more than VTH. Okay, that is the condition to make the MOSFET on. But here you can see the VGS is smaller than VTH. It is only 5 millivolt. So it is here. So it means the MOSFET is off. So we have to make on the MOSFET. Then only we can amplify our input signal. So for that we can add some DC voltage for biasing purpose of MOSFET. So the MOSFET can remain on. Okay, even when the signal is not present, that time also. Okay, and this signal can overlap on that DC voltage. Okay, so let's go and see how. Okay, so let me make the diagram. Okay, this is RL, and there is V out, V in, and this voltage is VO. Okay, and I'm keeping VO equal to VTH. Okay, this is our attempt first. This we are trying. And the value of VTH is equal to 0.5 volt. Okay, now I am making VGS ID graph. Okay, this is zero point 0.5 VTH. Okay, now the I'm making V in also 5 millivolt. Okay, and this is VGS. So VGS will become, apply KVL here. You will found VGS, then VGS equal to V in plus VTH. Okay, so let me plot VGS also. So this will be somewhere there. VTH means 0.5. Okay, that 0 will add it with this, so 0 will come here of V in. This point will shift to zero point 0.5 volt. Okay, and this point will shift how much? 0.5 plus 0.005. So 0.505 somewhere here, and lower will be there. So this point will be 0.505 and this point will be, we have to remove this, so it will be 0.495 volt. How? 0.5005 minus, it will be 495. Okay, so means, so this part of when the VGS equal to, sorry, V in equal to 0. Okay, when the V in equal to 0, that time the MOSFET will be on the boundary. When the VGS is equal to this much, means 0.505, I mean somewhere there. Okay, it is 0.505 volt. So means how much current will be there? So the current will be this much, ID 1. Okay, so okay, let's consider some values. The mu n cox equal to 100 micro ampere per volt square, and W by L equal to 10, and VTH is 0.5. Now calculate the ID1. ID1 will be equal to, see this region is what? I'm taking one different pen. Uh, okay, see this region is what? It is the saturation region. Okay, so we will use saturation equation here. So according to the saturation equation, ID equal to mu n cox W by L divided by 2 and VGS minus VTH square. So the mu n cox is 100 micro. Micro means 10 to power minus 6. And W by L is 10 and divided by 2. VGS is how much? VGS is, yeah, this is V in plus VTH. V in plus VTH means V in plus VTH minus VTH square. So this will be cancel out, and now it will be 100. Oh, this will become 10 to power minus 3, these three. Okay, this is divided by 2 into, sorry, this will cancel out. This is V in. VTH will be cancelled out. So V in is how much? V in is 5 millivolt. So it will become 25. Square of 5 will be 25. And milli means 10 to power minus 3. So it will become 10 to power minus 6. After division, it will become 2.1.12.5. This means current ID1 will become 12.5 nanoampere. Okay, so this value is 12.5 nanoampere. Okay, now I want the amplified output 50 millivolt, like this. 50 millivolt I want add output. Okay, the input was 5 millivolt. Okay, so I am making input also here. Okay, in green. Input was like this, 5 millivolt, and I want output 50 millivolt. Okay, so we have output is equal to 50 millivolt, which we want, and we have the ID equal to 12.5 nanoampere, and we can calculate by this two parameter RL. Okay, so see what was there. There was RL. So this is ground, there is RL, this is V out, plus minus. Okay, and the ID1 is 12.5 nano ampere, and then rest of the circuit, this MOSFET and all. Okay, so we can take this and we can calculate the V out. Okay, see, oh sorry, there the uh, current is flowing through this 12.5 nano ampere. Okay. Hmm. So means V out is equal to ID1 into RL. Okay. So RL will be equal to V out divided by ID1. What is the V out? V out is 50 millivolt, means 10 raised to power minus 3, and ID is 12.5 into 10 raised to power minus 9. So RL will become, this will become 440, sorry, no, this will become 4 into 10 to power minus 6, sorry, plus 6. This will go on top, and it will become plus 9, and minus 3 means minus 6. Okay, so it is RL equal to 4 mega ohm, which is very big. It will take a lot of space. Okay, so it's not a good option. Okay, so what can we do? If we can make this current high, then our RL can be reduced. Okay, and how we can make this current high? Let's see. We saw this ID. VGS. It was somewhat like this. If we can take biasing at this point, okay. So see, this current will increase as compared to this current 12.5 nanoampere at 5 millivolt. Okay, let's take somewhere here. Okay, so let me take another page. For this, let's give some zero point 0.9 volt for biasing. Okay, let's see what will happen. So let me make the circuit again. Mm, okay, this time VO equal to zero point 0.9 volt. This is V in, this is VGS, there is V out, and the ID current is going like this. Okay, so this is zero point 0.9 volt, and I'm making ID versus VGS also. Mm, this is VTH, which is equal to 0 0.5 volt. Now I'm taking 0 0.9. 0 0.9. Okay. Yes. This is equal to ID 0. 0 0.9 volt is the biasing. So this is the case when the Vin equal to 0, right? The VGS will be equal to 0 0.9 volt. Okay, so let's take this case and calculate the ID note. Calculating ID note equal to same. It is in saturation, so it will become mu n COX W by L divided by 2, then VGS minus VTH square. So the mu n COX was 100 micro, so 100 10 to power minus 6. W by L is 10. There is 2 and this is 0 0.9 minus 0 0.5 square. So it will be 10 raised to power minus 3 after solving this, and divide by 2 into this will be 0 0.4 square. So it will be 10 to power minus 3 divided by 2, 0 0.16 means 0 0.08, or we can say 8 80 microampere. This is 10 to power minus 3, and 3 from there we will take, and it will become 80 microampere. Okay, so this is 80 microampere. Okay, so now when we will give input, so this will shift up to 0 0.5. Okay, so it will become 0 0.9 plus 0 point, sorry, this will be 5 millivolt. Okay, I'm writing clearly. Okay, this is VGS. So this point will become what? It will become 0 0.9 plus 0, sorry, 5 millivolt, and this is volt. Okay, so this much is 5 millivolt. So at this point, the current will become ID1. Let's calculate its value. So ID1, same in saturation, same UNCOX means 100 micro and W by L divided by 2. VGS is what? VGS is 0.9 plus 5 millivolt means plus 0.005. 5 millivolt we can write like this, and minus VTH is 0.5 volt, and the square of whole will be equal to, this will become 10 to the power minus 3 divided by 2 into what? It will be 0.164. Now divided by 2, 0.082 means it is equal to 82 microampere. So it is 82 microampere. Okay. So now let's calculate the RL. Okay. So for calculating the RL, we have to take the ID, the difference of these two currents. That only we have to take. So RL will be equal to V out divided by 82 minus 80 microampere. Okay, means V out is equal to 50 millivolt minus 3 and below 2 into 10 raised to power minus 6. So let's divide it 25, and this will be 25 kilo ohm, which is good. Okay, so like this you can buy the MOSFET. Okay, so now let's go to the next page. So that's why the biasing is important. So some, see, the biasing is used for keeping MOSFET on. Okay, if the MOSFET is off, then it won't be able to amplify the input signal. Okay, so now let's go to the one observation. Let's see, let me ask one question. So this is ID and this is VGS, and this is like this. Okay, so V1 is somewhat like this. Okay, and one is there. This is V2. Okay, and the input when we will give, first is we are biasing with V1, second we are biasing with V2. So both case we have to see that what is the good case, what is the good biasing for the MOSFET. Okay, so okay, if I'm giving input signal, and let's see, let taking different color, this is change up to V1 plus delta V. Delta V is the distance, voltage change is delta V. So the change in current will be delta I. Okay, delta I1. And if there the change is delta V, there will also change in current, which is equal to delta I2. Okay, so which biasing is good? This one or this one? Okay, let's see. For V1, see what we want. First of all, we want high current difference. So that is our condition. We want high current difference. If this is high, then this is good. If this is high, then that is good. So let's see which one is the greater, delta I2 or delta I1. Okay, so if you want to calculate this, okay, if you want to calculate this, you know y equal to mx. So you can do y is del I1 equal to the slope at this m dot delta v. Okay, for this case, it will be delta I2 equal to m. This is m1. Let's consider this is m2 and it is delta v. This one. Okay, so see, this slope is greater than this one. That is m2 is greater than m1. Means delta I2 is greater than delta I1. Okay, so this biasing is good. This is good, but is there any disadvantage for keeping this biasing V2? Yes. If you are keeping this, then the current will be more. Okay, that ID will be more. Means it will take more current from the battery. Okay, and it means battery will discharge more it will consume. Okay, so that is the one disadvantage. So that's all about the biasing. Why biasing we need? So for making the transistor on. Okay, so like see, if we are keeping our input somewhat like this, okay, we did biasing here, and then there is VTH. Sorry, I'm making one clear figure. Okay, uh, this is VTH. Okay, this is V in plus VTH. V in plus VO means this is biasing voltage, this is input. Total it is VGS. Okay, and it is going like this and this somewhat like this. So see, for this the MOSFET will on, but for this part MOSFET will remain off. Okay, so MOSFET won't able to amplify this. Okay, if another case I'm taking, so how we should do the biasing? Okay, if this is VTH, we should keep it somewhat like this on top of this. So for this also MOSFET can on, for this also, this point also MOSFET can on, for this also. If this point will come down to this VTS, then MOSFET won't be on and it won't be able to amplify our input. So that's why the biasing is very important. Okay. Now the next is, yeah, the next topic is, see, we saw now, we understand the biasing, why we need the biasing. Okay. And for keeping the MOSFET into saturation region, that's why we need the biasing of MOSFET. Now let's go to the next topic, that is common source amplifier. common source amplifier. So, common source amplifier means we give input to the gate. Okay, this is V in, and we have to do icing also. Obviously, we have to do V0, and this is VDD, and take output from the drain. V out. Okay, so this is the common source amplifier configuration. In common source amplifier configuration, source remains ground, give input to the gate, and take output from the drain. Okay, okay. So here we want to calculate AV gain, that is V out by V in, and Z in and Z out, output impedance and input impedance. So three parameter we want to calculate. So for calculating gain, let's take small signal model of this. So while making the small signal model, make all DC voltage ground. So this will become ground, okay, and this will be short ground. And so see, the MOSFET is like this. The small signal model of MOSFET is this GM and whatever VGS is there. Okay, so this is V in, this is gate, this is source, this is drain. So at gate, you can see what is at gate. There is input voltage, so V in, okay, and at drain, there is one resistance, okay, that is RD, and then there is ground, and from T, from there, the D point, we are taking V out, means from there we are taking V out. Okay, that's all. And source is ground also. This VGS is equal to what? V in. Okay, so this VGS is equal to V in. So let's apply, we have to calculate V out. See, first of all, this GM VGS, so it will become GM V in, because VGS equal to V in only. Now let's apply the KVL. What? See, the current is going there. This current is going like this. Means GM VGS going like this. This is plus minus. Apply the KVL in this path. So V naught, and this is plus minus, means it will be plus, and I is equal to GM V in, and this is RD equal to 0. So V out will be equal to minus GM V in dot RD, means V out by V in, that is equal to AV, will become minus GM RD. Okay, or we can say V out will become, this is the gain. Okay, first thing, and V out is equal to minus GM RD V in. So V in amplified by this much, and you can see the phase difference of 180 degrees. Okay, so means if input is like this, okay, this is V, so output will be how? Output will be, okay, like this, amplified version of that. and this is GMRD dot V. Okay, so we have calculated AV. Now let's go calculate Z in. Z in will be equal to infinite because no current is going in this direction. Okay, there is insulator. So Z in is equal to 0. Sorry, infinite because no current is going there. So it is infinite. Now R out. So to calculate the R out, you have to make V in 0. That means we have to make short it. We short it. So VGS will become 0. Am I right? So this will become 0. So there will be 0. And you have to apply here Vx. And now you can calculate the child impedance. And this is I. Okay. So Vx equal to I dot R, right? There is RD, sorry, RD. So Vx by I is equal to RD. That is my Z out, output impedance. So Z out is equal to RD. Okay, let's go to the next page and let me write all observations. So from common source amplifier, we have calculated the gain, voltage gain, that is minus Gm dot Rd, the very first, and Z in, that is equal to infinite, number 2, and Z out equal to Rd, third. So this we learn from common source amplifier with resistive load. Okay, resistive load we are using. And we have seen biasing. So why we use biasing? So the MOSFET can remain in saturation region. Okay, so that's why we do the biasing, and for that biasing we give the DC voltage. Okay, so that's all for today. Thanks for watching the video. If you like the video, please uh, like and subscribe it. Thank you. Next we will see the common drain configuration here. Okay, and common gate also. Okay, thank you.